to your talk. So you must be really impressed, right, Qimiao?
Well, appreciate that.
So we'll blame Qimiao if the talk didn't go well, right?
Oh, wow.
Yeah.
Good.
I told my students to show up, so hopefully, yeah, they show up.
Okay.
Hey Jeff, good to see you.
Hey, how you doing?
Good. Oh, you guys still you know, idle, right? Nothing's happening with reactor.
Yeah. Well, I mean, they're working on it, but yeah.
They're working on it. Oh, but basically
they're making progress.
Right? I see. Are we expecting this year or next year?
No, I think not this year. That's,
okay.
Yeah.
Okay.
But maybe, yeah, I don't know. I mean, it depends on the Nuclear Regulatory Commission.
Okay.
So that I think they're getting the reactor back in shape so that they can actually run it. And,
okay.
And then what's going to happen is they're going to.
Oh. Somehow he's.
I think Jeff is frozen.
Yeah, he's frozen. Yeah. Okay, maybe you can start sharing your screen. We can get started. Yeah. Let me introduce you. I mean, wow. I mean,
wow.
Qimiao basically needs no introduction. He started the Frontier. You know. Oh no, he started RCQM at Rice.
I didn't do.
You didn't start at Frontier. Yeah. I think yeah. Tomo started that. Yeah. This looks great. Yeah.
You see my screen?
Yeah. Can you put it full view, and then you can put the PowerPoint down. Okay, so we're very happy today to have Qimiao to give a talk. He's sort of a local person. We typically don't have local person to give talks, but Qimiao had such an interesting result. I thought, you know, it's really interesting to get him to give his recent talk, recent result on this quantum criticality in metals. Yeah. Okay, so Qimiao, it's all yours. You know the format, right? Yeah.
Well, thanks, Punchen. Well, thanks, Punchen, for organizing this lively series of seminars. I'm very happy to be part of this. So the subject is quantum criticality, as Punchen announced. And here's the outline. I'll give a bit of a combination of a brief overview and some recent work on the quantum critical aspects of these correlated metallic systems, and this mainly to set up for discussing our recent work done with a number of collaborators on what we claim to be high TC, defining some particular sense that comes out of quantum criticality. If time permits, I want to spend just a couple of minutes giving the interest of Punchen and others on the flat bands. We've done some recent work making the connection of flat bands with the kind of things that I'll be mainly talking about. So, so here's a list of collaborators, particularly my just graduate PhD student, Hao-Yu Hu, who just left earlier this week or last week for his postdoc in Spain, and with Lei Chen and others from Rice, a few former student postdocs, Jed Pixley, Stefan Kirchner, and a long-term collaboration with Kevin Ingerson and his group at the University of Florida. We have standing collaboration on experimental, getting us grounded by interacting and collaborating with Silke Pasha and her group, and also by talking to a number of distinguished experimentalists. So just to get started, here's a plot courtesy of Joe Thompson, which attempts to connect different classes of strongly correlated superconductors with TC on the vertical axis, and T0, which at least for the heavy fermions has a meaning of effective Fermi energy. So TC by absolute scale for these F-electron-based systems is relatively low. TC for the cuprates is high. But if you make a plot like this, and you can draw a straight line with a slope of a few percent. So for the purpose of this talk, I will define high TC as those correlated superconductors whose, well, just superconductors whose TC reaches a few percent of some effective Fermi energy scale. And so that's one way to connect the heavy fermions, the cuprates, and the number of other materials. But there's another connection, which is that often the normal states of these correlated superconductors are strange metals, and so certainly in these heavy fermion systems, the normal state of many of these have T-linear resistivity, and so is the cuprate, and that T-linear resistivity showing up in many other classes of strongly, in the normal state of many other classes of strongly correlated superconductors. And but that's not the only thing. There's a slew of other properties in the dynamics and thermodynamics and Fermi surface properties, which are characteristic of such strange metals, and at least on the dynamic side, it connects with the spectroscopy community, which actually for us, that's where the motivation initially was given.
So Qimiao, let me sorry to interrupt.
Yeah, sure, please.
So where's the next type? I mean, iron-based superconductor 4 on this.
Yeah, Joe didn't put it on it. I didn't have the time to put on it. I think would be interesting to see whether it falls on this line. I have not
clear.
I have not done that exercise. It would be very interesting to do that exercise. Good. It's a good approach. Yeah.
Okay. Thank you.
Thanks. So now, referring to this strange metal aspect of a normal state, let's zoom in to focus on these heavy fermion superconductors. Heavy fermion superconductors qualify as being vulnerable. That's the setting in which the very first unconventional superconductor was ever discovered. And by now, this family of superconductors has grown to about 50 material members. So it's a very large family. And most of them, if not all of them, have some kind of antiferromagnetic correlations. And in the past 2 decades or so, there's a very big focus on the quantum criticality and strange metals. And I want to touch upon some of these understandings. But the main point I want to make is that these understandings of the recent past on the quantum critical and strange metal aspects has not yet been taken into account in understanding driving force for superconductivity, and the present work is we surmise as going along that direction. So quantum criticality, it's one of the things which I think we can say with the heavy fermion metals, some of which I will at least mention, is that the quantum criticality is well identified. And this is not just because there's T-linear resistivity. It's because there's the understanding of the phase diagram, temperature control parameter, temperature and a non-thermal control parameter phase diagram, but also based on thermodynamics. So at some years ago with Achim Walsh's group, we thought about the thermodynamic signatures of quantum criticality. And so the specific heat may have a particular temperature dependence, and but the ratio of something called thermal expansion to the specific heat, these are two quantities which both go to zero in the zero temperature limit, but their ratio must diverge if there's underlying quantum critical point. And that divergence has been seen but in quite a fairly long list of these heavy fermion metals. And one of the implications is that if there's divergence of gluonizing ratio, it implies that entropy is accumulated. If you stay at a low temperature, scan the non-thermal control parameter, and entropy is maximized near the quantum critical point. And there's a demonstration by a number of different groups. This one came from Hilbert von Lohneiser's group from the University of Karlsruhe, which looked at the response, the thermodynamics in the presence of different strain or stress, depending how you look at it. And one can extract that the entropy is maximized in the vicinity of the quantum critical point. So a larger entropy makes the electronic system to be very soft, and that's one way to think about the development, the tendency of developing unusual excitations and unusual phases at low temperatures. Now, one of the things that has come to be appreciated from studies of these quantum critical metallic systems and others is that there's a need of going beyond the framework of lambda, which is to describe the singularity at the critical point, and by extension, quantum critical point in terms of fluctuations of the order parameter. And that can be seen in these antiferromagnetic metallic settings. If you have the order parameter fluctuations associated with a particular wave vector Q, on the Fermi surface, it's only a small region of the would be connected by the Q, and those would be the regions, the hot regions that would lose the quasi-particles. So, but much of the Fermi surface would not experience this non-zero Q low energy scatterings, and therefore would stay cold. And so that much of the Fermi surface would retain quasi-particles, and something like electrical current would be primarily carried by these quasi-particles, which are much more long-lived than the region, the excitations that were in the case space where the losing quasi-particle. And so it would have a hard time to give something like T-linear resistivity. So how to go beyond the order parameter fluctuations? We'll have to think about additional critical modes that have the capacity of make quasi-particles lost on the entire Fermi surface. So let me go to this particular part, heavy fermion metals, which for those which feature antiferromagnetic correlations, and in the typical cases would be described by a Kondo lattice. So you can think of it as a quantum spin system and a conduction electron band in the simplest case that's glued together by the antiferromagnetic Kondo exchange interaction between these two species. Now, it has been a long-standing effort of the correlated electron community to recognize and to develop the formalism of describing the formation of quasi-particles from the Kondo effect, which imagine that the local moments, instead of forming antiferromagnetic order, they form a singlet with the conduction electrons as depicted by this qualitative picture. And you can think of the singlet as a kind of bound state form between the local moment and the particle hole triplet combination of the conduction electrons. So just like if I have a superconductor, I have Cooper pairs, which act as a kind of bound state. And if I want to describe the excitations, I can just break apart the Cooper pairs. And that, in the end, would give us the Bogoliubov-de Gennes quasi-particles. Here, I have this bound state formed between the local moment spin and the particle Hall triplet combination. So if I want to break it apart, I have several different ways. I can kick out an electron that will be a bare electron excitation that already existed before the two species are coupled together. But I also have the possibility of a composite object of a local moment spin and a hole in this case, but could also be an electron. And this object, spin one half, so can form a spin 1/2 combination and has charge E. So it has the quantum number of a bare electron. So that's in fact the composite fermion, which provides a basis for the heavy quasi-particles, and that's usually depicted in encoded in a mean field description of a conduction electron band like this dashed line, hybridizing with a renormalized flat level generated by which represents electron excitations generated by Kondo effect, and they form this hybridized bands with very large density states, and therefore the name heavy fermions. Now, so this is a established procedure of developing quasi-particles. The weight is very small, can be as small as 10 to -3, but it's non-zero, and that sets up the Fermi liquid description within a very narrow energy or temperature window that could be 3 orders of magnitude smaller than the energy scales of bare conduction electrons. But those are well-defined quasi-particles. So if we want to destroy the quasi-particles, one way to proceed is to mess up with the Kondo effect. And so that's in fact the picture that was advanced, namely if we tune the control parameter, and it could be thought of as this Kondo scale divided by the RKKY scale. When the Kondo scale dominates, we end up with the Kondo singlet ground state as depicted here, and that leads to the development of quasi-particles. And there's a scale which will characterize it, a low energy scale that will be non-zero. This is a scale which happens below the single ion-ish bare high energy Kondo scale, the onset of Kondo correlations. There's a development of fully developed Kondo singlet and quasi-particles. But if we get towards the part of phase diagram, which is established by having the local moments communicating with each other, and in this case, they form in the anti-ferromagnetic order, it would be detrimental to the formation of the Kondo singlet. And if this leads to the destruction of the Kondo effect, and if it happens at the quantum critical point, we have additional excitations that's critical associated with the destruction of the Kondo effect, or marked by this E star scale collapsing to 0 at the quantum critical point. And so I'll just very briefly mention the calculational scheme which we have employed. This some extended version of dynamical mean field theory. I'm not going to go through the process, except say includes local correlations and the anti-ferromagnetic exchange interaction between the different sites. And in this approach, the local correlations are captured by the Kondo coupling of the local moment with a fermion bath, and this RKKY exchange intersite correlations are captured by the local moment coupled to a fluctuating magnetic field bath. And so that's the procedure that we're going to use. The reason this was important, going beyond the possibility of developing the Kondo singlet and the quasi-particles. Oh, pinching, by the way, I can't really see the chat, so if there's anything, maybe you can alert me.
Yeah, I was getting, there was a question, how is the critical energy scale E measured? E star measured?
Yeah, so that's a very good question. I'll come to the signature part of it, but E star would manifest in several different ways, like the cutoff in the actually it was the most direct way would actually be measuring states, the probes that not just is in the spin sector, but also in the charge sector. So one of the effort which has been made was using the terahertz type of spectroscopy. But so far, what has been done was sort of Hall effect, which I will not actually show a plot, but it's there's a characteristic crossover. Let me just mention it. So if you scan, do an isothermal scan of the Hall effect, and if you can be sure that the Hall effect is primarily the normal contributions associated with the quasi-particles, then there's a very rapid, at the finite temperature, there's a rapid crossover. And the middle of the crossover is E star scale. And it delineates the regime where system is flowing towards a small Fermi surface ground state, and regime where the system is flowing towards a large Fermi surface ground state. So that's so far the most direct experimental means that the E star scale has been measured. Okay. So, but what I was going to say is that this procedure allows us to address the fate of local moment in the different parts of the phase diagram, because the local moment coupled to the fermion bath leads to the Kondo state, which is there's a renormalization group procedure that one can apply to analyze this most Fermi Kondo model. So there's this Kondo fixed point, but there's also if you tune the coupling to this bosonic bath, and that reflects the effect of RKKY interactions, you can destroy this fixed point, reach other type of fixed point. And if one, so in the end, there's a possibility of reaching this red fixed point. And this red fixed point is interesting because the black fixed point is where Kondo singlet characterizes the ground state, and the weight of the Kondo singlet shows up as in the weight of the quasi-particles. But if you reach this red fixed point, a number of different things happen, but the upshot is that the quasi-particle weight goes to zero, and in the lattice model, it will be the quasi-particle weight will go to zero everywhere on the Fermi surface. So for this post-Fermi Kondo model, one can do more. For instance, one can calculate the finite size spectrum. This is the collaboration with Kevin Ingerson group with a particular one of these models, where this red line describes the finite size spectrum at this red fixed point. And if you move away from the red line here, you go to a different spectrum. And here one could, if one were here, that eventually the spectrum can describe by a Fermi liquid form. But this red fixed point, this finite size spectrum, just additive quantum critical point would lose the Fermi liquid form entirely. And that's a characterization of the quasi-particle weight goes to zero. And also this is a critical point where all the energy scales have, it becomes a scale having a scale invariant spectrum. And as a result, KBT is the only scale in the problem, and the dynamics, one can probe a number of different physical quantities as a function of frequency and temperature to see that it has the scaling h bar omega KBT with a Planck constant in it. So that's a characterization of this Bose-Fermi Kondo model per se, and we can proceed with this understanding, proceed to analyze the whole lattice model, which whose equations I'm written down here, which I think I'll skip describing it unless there's a question. And that set of equations for the lattice model is the basis of showing this E star collapse into zero is like reaching the red fixed point in the Bose-Fermi Kondo model, and that happens at the antiferromagnetic quantum critical point. We can have other kind of solutions as well. That this is the overall phase diagram that I will for just for time considerations, I will not go into details. But in fact, I will not describe it. This phase transition, which I just described for you, having the antiferromagnetic transition coinciding with large Fermi surface to small Fermi surface like transitions, represents one of the possible trajectories, sequence of phase transitions in the zero temperature limit. One could also have other sequences going through an antiferromagnetic order with a large Fermi surface, which becomes folded, or a paramagnetic phase with Kondo destruction. And so this would have several stages of phase transition in the zero temperature limit. But what I will focus on, what I have focused on so far, and what I will focus on primarily in the remainder of the talk is this trajectory one. But a phase diagram like this, there is this Donier axis of Kondo versus RQKY competition, and a quantity which could capture, say, frustration of the magnetism has also been explored in a variety of materials, and I refer you to this article, which has provided a status report. So back to this trajectory one. What I want to do is just to mention three things as relevant, directly relevant to the experimentally measurable quantities. I already alluded to that the Bose-Fermi Kondo model has h bar omega over KBT scaling. In the lattice model, this would show up at the quantum critical point, and at the antiferromagnetic wave vector as the dynamical spin susceptibility as a function of frequency and temperature would have a form like this, where it has a singular frequency and temperature dependencies, and the collapse onto h bar omega over KBT scaling. So this type of scaling was which was the initial experimental contributions of Megan Aronson and the collaborators, and Elmer Schroeder and the collaborators, were in fact the initial motivation to consider quantum critical points that go beyond the order parameter fluctuations. And we spent the effort to calculate this exponent, especially in the Ising and isotropic case, and find the exponent to be indeed fractional, which was also the initial puzzle that was posed by the inelastic and neutral scattering experiment, and the value is roughly in the range that was seen in the experiment in cerium copper 6 slightly doped with gold. As we went on to go from this Ising case to the spin isotropic case as a model which we can study, there was a bit of embarrassment that it's not just the fixed point, red fixed point. In fact, there are many fixed points, and initially it was the purely numerical result, and more recently we have had analytical understandings about the fixed point, this multiple fixed points and the annihilation of the fixed points. But in the end, even in this SU2 case, we were able to determine to show that this h bar omega over kBT scaling does show up and with a fractional exponent. So that's one of the experimentally testable statement, and maybe in connection with the question about how is E star going to say it shows up in physical properties, one would not have this form of scaling if E star is non-zero. At least that's sort of the theoretical statement. So in that sense, the h bar omega, the kBT scaling is a manifestation of this destruction of the Kondo effect. The other is the large to small Fermi surface reconstruction across the quantum critical point. I already mentioned that when the Kondo effect dominates over the RKKY interaction, we have the Kondo singlet, ground state, and there are these composite fermions which are generated. One could, and then the Fermi surface enlarged. That's a large Fermi surface. But if one is on the left of this E star line, the physics is controlled by the ground state in which the Kondo singlet is destroyed. The static amplitude of the Kondo singlet vanishes, and the Fermi surface becomes small. So therefore, across the quantum critical point, there's a sudden jump of the Fermi surface, and across, if it's a finite temperature, finite energy, would be a rapid crossover between these two regimes. And so one way to think about the destruction of Kondo effect beyond the pictures is that when the E star scale is non-zero, it shows up in the particular form of the conduction electron self-energy. This epsilon F star is actually familiar. That's the basis of the renormalized bands picture. But the weight of this E star scale would show up in the weight of this pole of the conduction electron self-energy. And once you have a pole in the conduction electron self-energy, there will be, in the end, the single electron Green's function will have two poles capturing the two renormalized bands. The mean field picture I already showed you earlier. And so if there's a destruction of the Kondo effect across the quantum critical point, this was actually a prediction that was made early on, that there will be a large to small Fermi surface transformation sharply, at least in the zero temperature, it would be sharply across quantum critical point, and at the finite temperatures would be a rapid crossover. So I already mentioned that for ytterbium, rhodium-2, silicon-2, there has been extensive Hall measurement by Superconductivity and Frank Stagish and their collaborators. This has been also now been analyzed, measured and analyzed for some other heavy fermion materials, also identifying this E star and the T star scale. And in the 115 systems, in particular, cerium, rhodium, indium 5, as a function of pressure, this Fermi surface jump across a second order quantum phase transition has been observed by quantum oscillation measurements. I have the plots in the slide somewhere, but let me just make a statement. And also, there's a number of articles at various stages which summarizes the status of this rapid change and extrapolated jump of the Fermi surface across the quantum critical point. And so this is this describes what happens going across the quantum critical point. at the quantum critical point, this pole strength approaches zero as one tunes the system from the paramagnetic side, and so the quasi-particles would be completely lost on the Fermi surface, and that has been probed in a number of ways. There has been effort made by the Wiedemann-Franz ratio measurement and a particular type of analysis, which I subscribe to, leads to a 10% violation of the extrapolated zero temperature limit of the Wiedemann-Franz ratio, which provides some evidence for the loss of quasi-particles in the case of ytterbium rhodium to silicon 2. But there's a very striking, in my opinion, striking experiment. I'm involved in this, so maybe I'm not really entitled to say that, but it was the primary work of Dagnato Sen's group measuring the noise using the MBE films made in Vienna by Superconductivity group. And so the point is that if you have quasi-particles, such as in a case that we have no doubt, such as in the gold, you would see a particular value of the current noise, and if you measure, if you scale that by the current from this factor called Fano factor, and in the regime, in a particular regime that's of relevance to gold, it would be 1/3, and we believe that if there are well-defined quasi-particles, it would be 1/3 or even larger if it's in a different regime of the disorder versus interaction strength. While in ytterbium rhodium to silicon 2, in the temperature range that has been measured, that falls in the quantum critical regime, it's the Fano factor is substantially smaller than expected 1/3 or larger value. So that's that is at least to me is a very striking evidence for the loss of quasi-particles in the quantum critical regime. Okay, good. Yeah.
Where does superconductivity comes in? I mean, a lot of the materials, have superconductivity, right, near the quantum critical point. I mean, in your model, does
yeah. So this is all sort of the setup for discussing quantum superconductivity. So okay. If you pinch in,
sure. Be more patient. Yeah.
In 2 slides, I'm getting.
Okay.
But the point that I want to say is that in these quantum critical systems, there has been systematic efforts made to probe and analyze and understand different aspects of singular properties. And so this is a last piece of the normal state information before I get to the superconductivity. And so that's the h bar omega of the KBT scaling that I already mentioned for the spin responses. And this is a data of terahertz spectroscopy. Again, in ytterbium rhodium to silicon 2, it's a terahertz spectroscopy measured in John Kondo's lab using the MBE films provided by Superconductivity group from Vienna, and some transmission measurement. And within the frequency and temperature window that can be accessed, one sees that the optical conductivity follows this h bar omega of the KBT scaling. And so we interpret this as saying that the quantum criticality, even though it's a magnetic quantum critical point, the charge degrees freedoms are also involved. And that's precisely what one would expect based on this additional critical modes associated with the destruction of the Kondo effect. And so the very large amount of quantum critical fluctuations in which one would think that is primarily in the spin sector, because these are local moment based systems as described by the Kondo lattice model, and as the entropy that's measured in the quantum critical region testify that there's a very large amount of quantum critical fluctuations, very large spectrum that's manifested in the quantum criticality. This experiment is significant in a number of ways. Microscopically, we believe that it shows that there's even though the Kondo effect in the static sense is destroyed, in the fluctuation sense, it's still operating. But importantly, this very large amount of quantum fluctuations also captured would also be manifested in the charge sector. And so that's my sort of transition to discussing superconductivity, because these critical fluctuations would influence the charge sector, and by extension could be expected to influence superconductivity in an important way. And given that the fluctuations has a large spectral weight, one may expect that the superconductivity that develops would be very robust. But to actually theoretically describe it, we cannot just use the post-Fermi Kondo model, because if I have just a local moment, I cannot write down a unconventional pairing functions. So we've extended the formalism to a cluster version of this coupling at a minimum to local moments which are anti-ferromagnetic coupled and with each other, and they are in turn coupled to this fermionic path through the usual Kondo coupling, and also the bosonic path through the feedback from the RQQI couplings with other local moments. So the equations are similar to what I wrote down earlier, but it shows up in a cluster form. And so the first thing we want to check is that in this cluster form of the analysis, the conclusions that we have reached about the normal state, the quantum critical aspect, remain intact. And we indeed show that this dynamical KBT scaling, the large small Fermi surface reconstruction, lots of quasi-particles at the quantum critical point remain. So I just want show the result of this cluster EDMFT calculation for one aspect, which is this E star scale, still collapsed to zero at the onset of anti-ferromagnetic order. So the same type of quantum criticality is being captured with a large to small Fermi surface sudden reconstruction at the quantum critical point. But also in the dynamics, the omega over T scaling, here it's the Monte Carlo calculation, so it's the imaginary Matsubara frequency, but the spin response at the anti-ferromagnetic wave vector, it's singular and with exponent, which is approximately same as in the previous calculation, and has the omega over T scaling. So that sets the basis for analyzing the superconductivity. So what we first did was to get a sense of whether superconductivity can develop. And so let's just take this cluster model and analyze its phase diagram first in a normal state. So there's a regime where the local moments are all Kondo spring forming a singlet through the coupling with the fermion path. The Kondo effects completely destroyed. That's this part of the phase diagram for the cluster model. But also in the model, there's a phase which we label as intersite singlet as a standing alone phase. But importantly, that phase itself is not particularly important for our purpose. What it does demonstrate is that even everywhere here, there's a short-range spin singlet correlations. And this turns out to be very important in promoting pairing correlations and in promoting particular channels of pairing correlations. So we take a scan around this, which again has the Kondo versus RQ driven dynamics competition. And so this dashed line is scanned here, and starting from high temperature go to lower and lower temperatures. And we can see that spin singlet pairing correlation, the spin singlet spin correlations and the spin singlet correlation in a normal state, as caused by the RQKY interactions, would promote the spin singlet pairing correlations that becomes larger and larger as we get closer to the transition. And one can check that, for instance, the triplet channel, the pairing correlation is suppressed by this kind of correlation. So all these are consistent with the short-range spin singlet correlations in a normal state that this quantum critical system has that is promoting the pairing correlations. And then we can do the lattice calculation, see where the lattice pairing correlation becomes, susceptibility becomes divergent. That identifies as the TC. And TC, we reach a conclusion that in the quantum critical regime, which has this Kondo destruction type of quantum criticality, superconductivity exists in this calculation and comes out to be a few percent of the effective the bare Kondo scale. So in that sense, it's a few percent of the effective Fermi energy, and that's our notion of high TC. It's actually not just our notion. The experimentalists in this heavy fermion superconductivity community has defined this notion since some time ago, but I'm certainly not aware of prior theoretical analysis reaching such a conclusion. So I just want to compare one with one particular system. That's the CN-rhodium indium-5. I have mentioned earlier that the quantum oscillation measurements show that as a function of pressure, the system, which has a second-order magnetic phase transition, which one can see by suppressing superconductivity using a relatively modest magnetic field to identify magnetic and non-magnetic phase transition. The quantum oscillation frequencies show a sudden jump across this critical pressure, which is roughly 2.3 or 2.5, somewhere around 2.5 GPa. And so this is the phase diagram of anti-ferromagnetic order and the TC. And in fact, I've switched my phase diagram around just for the purpose of comparing with this plot, which had been made by experimentalists, which was very natural because the ambient pressure of the system is an anti-ferromagnet. So GC over the bare Kondo scale for 115 around critical pressure is somewhere around 5% or so. So we surmise that we capture the same order of magnitude. We can also compare with other systems like silicon copper to silicon 2. In that system, the E star actually is non-zero at a quantum critical point, but there are experimental indication that E star nonetheless is small compared to the Kondo scale. Kondo scale is somewhere between 15 to 20 Kelvin for silicon copper to silicon 2, and the E star or T star is roughly somewhere between 1 and 2 Kelvin. So even in that case, this Kondo destruction type of quantum criticality that has the forming of T-scaling Fermi surface going from small to large, and all these features and lots of quasi-particles still would dominate the driving for the superconductivity. And we did a calculation in a slightly tweak the model for that and get TC of about 2% of the Kondo scale. So maybe I think still have a few minutes. Let me just make two quick points. One is that it appears to us that with the lessons we've been learning about the nature of the normal state, the quantum critical state with strange metal properties, and its effect on superconductivity could have connections with what's going on in other classes of strongly correlated systems. So, for instance, in the cuprates in 214, there have been recent experiments that provide evidence for a Fermi surface reconstruction near the quantum critical point, the existence of quantum critical point, or at least not too far away, the system in the optimal Doppler regime not being too far away from quantum critical point. That we heard from a very nice talk by Stephen Hayden 2 weeks ago in this series. And so that, and also in the YBCO, there's a quantum oscillation measurement showing the tendency of the mass, which is divergent, which the quantum oscillation measurements in 415 that serial order linear 5 that I mentioned also provide evidence for the cyclotron mass to show the tendency for divergence. So while in the general sense, whether the Hall effect really provides a phase diagram like this with small to large Fermi surface change, I think that it's still an ongoing debate in the cuprate context. Perhaps there's at least in the broad stroke sense, there's some connection to be made that this delocalization localization feature associated with Kondo destruction in these heavy fermion systems may also have be relevant to some extent for the cuprates, and the organics have from Hall measurement have also shown features like this, and the ion-based ion chalcogenide superconductors FETSE, Ming Yi's group has done a systematic analysis of FETSE and provides some evidence for the large Fermi surface reconstruction across that series. Now, I think I still have a couple of minutes. Is that Panchen? Is that okay?
Yeah, maybe we can talk like 3-4 minutes maybe.
Yeah, that's more than enough. So I just want to very briefly, because this is something that we very recently have done, and I think there's a lot of interest on flat bands. There's also a lot of comparison between flat bands in the kind of systems which are being discussed with heavy fermions, which naturally have very narrow bands. But there's these flat bands could be a new setting for strange metallicity. So just very quickly, this was done that the work that has just been written up with Hao-Yu Hu. And the motivation came from two experiments. One is from Joe Tchaikovsky's group in nickel 3 Indian. I think I hope got the formula right. That showed have evidence for flat band and wide bands and T-linear resistivity. This is the work from PSI, Gabriel Play, So on ion tin, one of the ion tin family members that have from RPES, which is some indication for strange metal. So this made an impression on me, and we thought we would think about such systems. There's also a large effort, at least effort made by the theorists working on Mori systems, which also have strange metal features of mapping those Maury bands to Kondo lattices, and I refer you to some of the representative works here. So we thought we would think about a lattice which is sufficiently simple, even simpler than Kagame, but to have the features that these flat bands and wide bands exist, and the flat band would be topological, and the topology makes the real space description of these bands to be actually non-trivial and genetically considered to be very hard. So this is reflected here, for instance, in this particular lattice, which has a mirror symmetry, and these plus or minus ones are the mirror eigenvalues, and the fact that this green band, for instance, has this value which is changing across the high symmetry momentum points is a characterization of the topology. And then there's also a wide band, which just it's a toy model, just to make a point. So in spite of this topological non-trivial nature of the bands and the usual obstruction that it imposes on forming the real space, for this case, we were able to construct the Wannier orbitals, which for these Wannier orbitals, which primarily capture the flat band, it forms a triangular lattice sort of embedded in this lattice, and these are especially localized Wannier functions. And we went through a sequence of controlled mappings to end up with a description which has a conduction electron band and some Heisenberg RKKY interactions described by here, with local moments and a Kondo coupling, and on top of that, a Hons coupling. So we analyzed that problem. I will refer you the details to this preprint that we end up with essentially orbital selective Mach transition, where the large Fermi surface phase shows up at the Hubbard interactions, which would be large compared to the width of the flat band, but all these transitions happening when the Hubbard interaction is still small compared to the bandwidth, the width of the wide band. And this orbital selective Mach transition is the small Fermi surface phase, which large and small Fermi surface is depicted here. The mechanism of large to small Fermi surface is in this Kondo lattice language is very similar to what I have gone through for the usual Kondo lattices. And so this provides, we believe that provides a starting point to think about the normal state properties and strange metal aspects. And so with that, let me just summarize. I talked about the quantum criticality, in particular in these Kondo lattice systems on Kondo destruction that allowed us to understand this h bar omega of a KBT scaling that was first seen experimentally in inelastic neutral scattering measurements. And it has that feature with reasonable values of exponent that we can calculate. It has the large to small Fermi surface reconstruction that has not been tested by Hall measurements, quantum oscillation measurements in some of these heavy fermion materials. And there's a loss of quasi-particles, which to some extent is still being tested experimentally. And the main part of the work that I described is the superconductivity that's driven by such quantum criticality, and we end up with a TC, which is a few percent of the Fermi effective Fermi energy, as opposed to the BCS case where it would be 10 to the -4. And I talked about a connection with cerium, rhodium, indium-5, but there's also connections with other quantum critical materials in heavy fermions, which I didn't really get into. And I alluded to very quickly that maybe there's more to come, or at least it's profitable to think about not just flat bands, the interactions within the flat bands per se, but in the spirit of the Kondo lattice, heavy fermion systems, flat bands, and typically topologically non-trivial flat bands, which are coupled to wide bands. And there could be some related physics that could come into play. And there's already some experimental indications along that direction. So thank you very much.
Yeah, nice talk, Qimiao. Yeah, any questions for Qimiao? Let me ask first. Yeah, so you alluded the possibility of suppression, anti-ferromagnetism, and then you get to another phase, and then you said some materials may have superconductivity, but from experimental perspective, do you have any sense as to which potential materials, why some materials would have superconductivity whereas others do not have?
Yeah, so
maybe that's a tall order.
Yeah, so that's a hard question. In some sense, we've done the first work, and there's more systematics to address questions like this. But so the short answer is we haven't really thought about it. There's one aspect we did think about, which is that the anisotropy in the spin space could affect at least the nature of superconductivity if it develops. So for instance, let me actually, it goes along that direction, but I think we are a long way from answering your question. So let me just mention one thing. So can I get this back? Okay, good. So there have been large effort so I talked about CN115. I mentioned CN copper to silicon 2. For the normal state, I mentioned it quite extensively in ytterbium volume to silicon 2. And up until 5 years ago, the puzzle was why there's no superconductivity at all in the system. Now, it was understood that this is a field-driven quantum critical point. So the magnetic field, which is driving quantum criticality, would also be detrimental to superconductivity. So then the efforts were made by a number of groups to go into sub-millikelvin scales, and superconductivity has been evidenced, even in the state of quantum critical point. But there's more. There's some evidence that the superconductivity that's happening in the immediate vicinity of field-driven quantum critical point could actually be spin-tripled. And we thought how within this approach, this can possibly happen. And we realized that going beyond SU2K, spin isotropic case, if we go to this Ising anisotropic limit, and combining with the effect of field, we can at least get the possibility of a spin triplet pairing. Now, that's one knob. One could imagine tuning that influences the outcome for the superconductivity, which is degree of spin anisotropy. There could be other features that could affect both the quantum critical point and the superconductivity that it promotes or doesn't promote. And so maybe this is for a few years from now.
Okay, yeah, thank you, Qimiao.
Yeah.
Any other question for Qimiao? Yeah. It's a little bit difficult for the experimentalists, but I can basically understand your sort of a basic argument. Yeah. Any other question for Qimiao? Just raise your hand. Yeah. Okay, raise your hand. Yeah. Okay, go ahead. Yeah.
Hi, Qimiao. I wanted to return to my question from earlier from a different angle. I suppose you answered the question experimentally. Now, if I think of a critical energy scale, an energy scale that goes critical at the Kondo destruction transition, I should be able to see that from 0 temperature So for example, if I'm doing quantum Monte Carlo, I have an exact solution at zero temperature, I'm going through the tuning parameter. Is there, how can you get the E star from an exact quantum Monte Carlo solution? If you have the Green's functions, how do you get that E star energy scale from the zero temperature Green's function?
Yeah, so far our operational in our calculations, thanks for the question. I think I have a slide, but so far we primarily looked at going across the quantum critical point, what happens to the spin susceptibility, including the local spin susceptibility that's part of these equations. And so if the E star scale is, so let me first address the question of whether E star is zero or non-zero at a quantum critical point. So if the zero temperature limit of the local spin susceptibility is finite, then the E star scale is finite.
Okay.
Because the Kondo effect has to happen. If the local spin susceptibility at the quantum critical point diverges in the solution, then the E star scale collapses to zero at the quantum critical point.
I see.
So that's the easiest diagnostic in our calculations for what's that also, you know, I mentioned that you could have this type 1 type of trajectory and a type 2 trajectory, etc. That's what we sort of the easiest thing to do. Then you can analyze the Green's functions, which is harder, much harder to analyze the pole in the single particle Green's function. But it's part of because I know what the equations describe for the local moment coupled to the fermionic and the bosonic basis, and all these different quantities are coupled together.
I guess naively, when the antiferromagnetism breaks down, why would I not expect the susceptibility, inverse susceptibility to go to zero?
So the antiferromagnetic susceptibility always diverges.
Right.
At Q equal to ordering wave vector, but the Q summed the local spin susceptibility does not have.
Okay.
So that's the way to differentiate between the two classes of solution.
I see. So the critical energy scale on the Kondo side has to come from the local susceptibility.
Correct. Yeah.
Is your okay? Thank you.
Yeah. Any other question? Okay. Well, let's thank Qimiao again.
Yeah, thanks.
Hey, Jeff.
Yeah, my laptop just went to sleep.
Oh, your laptop just went to sleep.
Yeah, just as I was answering. Hopefully, we'll get back in some kind of operation early next year.
Okay.
That's the hope. Unfortunately, it's going to be because we now don't have enough reactor operators. The plan is for 4 cycles to run just for 4 days a week, and then shut down.
40 days a week.
4 days a week, yeah. So that
Oh, I mean they shut down on weekends?
Yep. So.
Wow, that's a good life for graduate student.
Well, it's a good life for instrument scientists and senior scientists too. It turns out, yeah.
Well, but that's assuming.
So the plan is to run for 4 cycles, or maybe even 5 cycles, and then they have to shut down to replace the control rod. And at that time, they're going to go ahead and put the new cold source in. So the installation of the cold source has been delayed, and the plan is to come up as soon as we're allowed to come up.
Okay.
But that's up to the Nuclear Regulatory Commission.
Are they very slow?
Well, I don't know if they're slow. They're certainly cautious. I mean, this was a major accident. So
really, I thought it was there's no leak, nothing like that, right?
No, that's not true. I mean, it was
Really?
they melted fuel,
I see.
so there was the whole facility inside was contaminated, and you know you know, so it was a major accident.
Okay. Okay.
So you know, and in fact, part of the difficulty with the Nuclear Regulatory Commission is this has never happened